So I want to talk a little bit more about compactness. That's what we've been doing, and that's what we're going to continue to do until the very end. I thought it might be fun to have a little warm-up. So my goal for today, and I'm not sure we're going to make it all the way. I think so. Our major goal is the Heine-Borel Theorem for today. The Heine-Borel Theorem, and it says in Rn, a set A is compact if and only if A is closed and bounded. This is the Heine-Borel Theorem. It's for sets in Rn. Compact is the same as closed and bounded. And I will refresh our memory about compact. Remember, compact means any open cover has a finite subcover, right? So the Heine-Borel, any open cover has a finite subcover. The Heine-Borel says in Rn that covers open, cover finite subcover property is equivalent to closed and bounded, which is a much more, in my opinion, this is a much easier concept to understand than this open cover finite subcover business. But they're only the same in Rn. In other topological spaces, compactness is different from, in other topological spaces, there's usually no such thing as bounded because you need some special notion about distances or whatever. All right, this is our goal. We have made some progress towards this already, but I thought maybe we could talk about one little piece of these as a little warm-up. I would like it to encourage you all to think about. I'll call this a warm-up. Let's show that A is compact implies A is bounded. In Rn, right? I should say a subset of Rn. If it's compact, that means it's bounded. Remember, compact means any open cover has a finite subcover, and I will give you one hint. This is sort of a one picture hint of the proof. A is whatever it is. I will draw a picture of one of our favorite covers to use. We did a bunch of examples of compact sets or sets which are not compact, showing them that certain sets are not compact by inventing certain covers. This is a cover using balls around the origin. These are sets that look like B of 0, n. That's the zero vector, that is the origin. So this is the ball centered around the origin with radius n, where n is just increasing to infinity. If you take all of those balls together, it's an open cover. I would like to demonstrate that A is bounded whenever A is compact. Anybody feel like you can say in this example, if A is compact, assume A is compact, and then use this cover that I'm talking about. O is the set of all balls of various radius. Any thoughts about this? Can you say, why does this mean A must be bounded? Of course, bounded means it doesn't go out to infinity. The fact that it's compact. Anybody got any ideas? Julia or non-Julia? Yeah?
Is it because there's a finite amount of balls that contain within it, then it's like a certain end that bounds it?
Yeah, right. If it's compact, it means only finitely many of these balls are necessary to cover up A. But since they're all sort of nested, right, that just means that there's some biggest ball that actually contains everything. And that means that it's bounded, right? That's what bounded means in R2 or Rn or whatever. It means the whole set can fit inside of a ball with a finite radius, all right? So assume this is compact. Use this as the open cover. Use this as our open cover. Then O has a finite subcover, but just because of the way that O looks, if I say you only need finitely many of them, actually that means you only need one of them, like one really big one. You don't need to stretch out beyond a certain one big one. So then O has a finite subcover. So actually, A is a subset of one big ball. All right, there's one kind of biggest one that actually you can fit the whole set into. And that means it's bounded. That's what bounded means in Rn. It means that it fits inside of some finite, but perhaps very big ball. So actually this is in a ball, so A is bounded. All right, this is like one little piece of the Heine-Borel, right? The Heine-Borel in general, remember, says compact is equivalent to closed and bounded. So we just showed, so compact implies bounded, right? This is in Rn. This proof only works in Rn because it requires that you use these balls. And so it may not work in some other space. All right, so compact implies bounded. We also need to show compact implies closed, and we also need to show the converse for those, that if it's closed and bounded, then it's compact. So that's what is in our future today. All right, we have, this is the first step in the journey. Any thoughts so far? Compact implies bounded. All right, let's try compact implies closed. Actually, some of these facts don't require Rn. This one you have to be in Rn in order to talk about these balls, because the general topological space doesn't have those kinds of balls. But some parts do not require, don't require that it be Rn. And let's do next, I want to do compact implies closed. And actually this is true more generally. I'm going to write this as a theorem by itself. This is true in any Hausdorff space. It doesn't have to be Rn. So if X is Hausdorff, then A is compact implies A is closed. That's the next step, right? We already know compact implies bounded. This is compact implies closed. And that actually works in any Hausdorff. I was just talking to my pal Mark Demers the other day. I told him I just learned this thing, Hausdorff. It means housed off. He was into it. All right. It means housed off. Okay. A is compact implies A is closed. All right, let's see if we can make this happen. This one is a little tricky. It's not clear immediately what Hausdorff has to do with anything, but you know, we want to show so that well, I'll say assume that A is compact. All right, and I want to show A is closed. What's a typical way to show something is closed? Usually it's most convenient to just use the definition. Anyone recall the definition of closed? What it means to be closed? Is, yeah? The complement is open. Yeah, that's what closed means. So I want to show A is closed. I will say, i.e., X minus A is open. That's what we have to demonstrate. And how do you show something is open? There's actually a few different ways you would typically show something's open, but it's most convenient in this, for this proof, to choose a point in this set and then show that it has a little neighborhood which is contained inside the set. That's typically how you would show a set is open, like in real analysis. That's usually how you do it. So I am going to choose some point. I'll call it X in this complement, X minus A, and then we'll find a neighborhood. Maybe I'll call it U in X minus A with X in U. That's the idea. This is how you show a set is open. I mean, this is one way to do it, by choosing a point. Now, I actually kind of like the idea of choosing a point because at some point we're going to use the fact that X is Hausdorff. And in order to say, I mean, what Hausdorff means is all about specific points and how they can be housed off, as they say, as my friend Mark Demers says all the time now, since I told him about that. Right? So yeah, this is you know, I don't mind talking about a specific point. That's all I'm saying. So the picture that I have in mind is something like X is like my whole universe. I have my set A, which is assumed to be compact, and then I have this point, little x is out here, right? It's not in there. And our goal is to create a little neighborhood around x, which is also all outside. It's all in the complement. This is what we're trying to do. This is a little tricky because it's not really obvious how to make that neighborhood U. And what does anything have to do with compactness? We have to use compactness, which is about any covering of A has a finite subcover. But this picture so far, there is no covering in sight. So you have to, unfortunately, kind of invent something out of nowhere to get yourself going in this proof. And actually, what it takes is I'm going to look at each point of A individually. Now, you could cover A just by covering each one of its points with a little neighborhood. And this is where the Hausdorff business comes in. So if I have a point here, call it a little a in there. And of course, we're going to do this for all the little points around there. But for each a in the A, since x is Hausdorff, here's where we use the Hausdorff. Can anyone say what that means? Hausdorff is all about 2 points, but now I have 2 points on the picture. So what specifically does it mean here? Yeah.
There is an open neighborhood around A and X that the union is empty.
Yes, the intersection is empty, she means. Yeah, there's a neighborhood around A and there's a neighborhood around X, so that those two neighborhoods are disjoint, right? They have empty intersections. So I'm going to say, since X is Hausdorff, I'm going to try to write this carefully. There exists, come on, two neighborhoods. I'll call them UA and VA, where the U the V is around A, the little a here. So this here is VA, and the UA is around X. All right. This set that I wrote before, U, is what we are trying to find eventually, which excludes all points of A. But from the outset, all we know is that there's a set around the little a and a set around the little x, so that those two sets are separate. So there are neighborhoods, UA, VA, with, I'm going to try and just write what I indicated in the picture. X is in UA, the little a is in VA, and their intersection is empty. UA intersect VA is empty. All right. And the idea is you do this for every point in A. So what you end up with, so do this for all A in A. I'm going to try and draw this picture so that it looks a little nicer. What you end up with is, here's my A, right? Every point in here gets a neighborhood around it. So actually, these guys, these are the V's. They will end up making open cover of A. They might stretch out beyond the boundaries of A a little bit, but these guys over here, these are all the VAs are an open cover of A, right? What do all the U's look like? The U's, every one of them is a different neighborhood of X. And this is a little bit of a pain, but they all look like this. Each one of these is including X. So these are the UAs, all are neighborhoods of X, right? I mean, we said this up here, right? For any of the A's, there's a A which is in the V, and then X, which is the same point every time. There's one specific X. So all the U neighborhoods are around X. All the V's are around the A. Yeah?
For all the neighborhoods that you put around with the different values of A, are those all going to be disjoint as well? Is that next?
No, not necessarily. Disjoint from one another over here?
Yeah.
Yeah. They will not. Each of these neighborhoods is disjoint from the corresponding one over here.
Okay.
They come sort of in pairs. Each one, just like up there, I only drew, come on. I drew one of them over here, and it comes together with one over here. So each one over here has its sort of twin over here, and those two are disjoint, but the different ones over here might overlap with one another.
Even if they're different like points within X, though?
Different points.
Like, because A has multiple, isn't A a part of X?
The big X?
Yeah.
Yeah.
So, since it's faster when each point within that have neighborhoods that don't intersect.
It's true, yeah. There is a neighborhood, for any two different points over here, there are neighborhoods that don't intersect. That's true. But I'm using the Hausdorff property for a point over here versus X. Actually, it's not possible to make it so that all of these neighborhoods are disjoint with one another. But each one is disjoint from one over here, all right? How are we gonna get, so this is what we have. What we want to end up with is one neighborhood around X, which is disjoint from all of these, all right? It seems to me, is there some way we could combine all of these sets to make one, maybe like, I don't know, the smallest one? Is there like a little guy here that is inside of all of those ones? That would be actually the intersection. So it would be a good idea to take all of these ones that we end up with and look at the intersection. Since each one of these is disjoint from each one of these, we take the intersection of all of them. Maybe that's disjoint from everything in A. That's the whole point of this. We want one single little open set here which is disjoint from everything in A. So what I would like to do is, I'm going to write this sort of as a sidebar because there's a slight problem with this, but we'll want to take the intersection of all the UAs. This is the intersection across all the A's. The intersection of the UAs. And this is what I want to call my sort of neighborhood that I'm actually looking for in the very end, which is what I'll call U. I want to take this as our neighborhood. All right. The intersection of all the UAs. Now, this is a good idea. The problem is, this is a bunch of open sets. The UAs are all open sets, and I'm taking the intersection of all the open sets. Is that a true fact that the intersection of a bunch of open sets is always an open set? Actually, that is not true. In the definition, this is an old fact that I hope you remember, the definition of a topological space. Any union of open sets is an open set, and any finite intersection of open sets is an open set. This, unfortunately, is not necessarily a finite intersection. That's the problem. So we'll want to take this as our neighborhood of X, right? But that is not a finite intersection. It's not. The problem is, like, the amount of sets I'm using, this may be infinitely many sets. If it was only finitely many sets, then everything would be fine. But it's not a finite union. So this U may not be open. Intersection, yeah, thanks. Well, it's also not a finite union, but yeah. It's not a finite intersection is what I mean. So this U may not be open, right? That's the problem. Anybody see a solution? Actually, there is a solution to this little problem. The fact that this is, when I say just take all these guys and make the intersection of all of them, the problem is there's infinitely many of them, and so the intersection may not be a open set. There's one piece of this, our assumptions about something or other, which I haven't used yet. Yeah?
A is compact, so there's a finite subcover.
Yes, A is compact. We never actually used that fact. What does it mean that A is compact? It means only finitely many of these suffice to cover A. And that means they have only finitely many twins over here. And if you take only those guys, then everything will work exactly the way you want it to work. So it is actually not necessary to use infinitely many of them over here, because we don't need infinitely many sets in the first place. We only need finitely many. So I'm going to try and write something like that. This is the basic idea here, which doesn't exactly work on this picture, but it does work once you make the finite subcover. So I will say, since A is compact, there is a finite subcover of the V's, right? The VAs. So actually, it's not, you don't need all those red guys. You only need finitely many of them. So I could say A is actually covered by, let's just give them names, V1, V2, up to Vn, right? You don't need a little neighborhood around every single point. You only need finitely many of them. But then we take the corresponding finitely many u's around Vx, and we make those the intersection of that. And so we have A is covered by finitely many of these, and then X is in the union of the u's, the corresponding finitely many u's, U1 up to Un. So let U be the union of these, I equals 1 to N of the Ui. Then X is in U, and U is disjoint from A. Because the U was constructed by doing that Hausdorff property over and over again. And if I take the intersection, each individual U is disjoint from one of those V's. And if I take the intersection of all of them, it will be, I mean intersection. I wrote unions again. I mean intersections. Intersection, intersection. Sorry about that. And this U is disjoint from A because U is made up of the intersection of all these, and each individual one was disjoint from a piece of A. And so when I intersect them all, it's disjoint from A. And that's the set we want. So I said U intersect A is empty, but that's the same as saying U is a subset of X minus A, which is what we wanted. All right. This is, in my opinion, a non-obvious argument, but hopefully once you sort of draw the pictures, it makes some kind of sense. I'm trying to scroll the picture back into view. I hope you can still see. All right. You cover by a bunch of individual little sets, but because it's compact, you only need finitely many of them. All right. This, in my opinion, was the hard part of what I wanted to do today. So the rest of it is considerably easier, I think. Any thoughts about this, though? So what can I refresh our memory? What we've shown so far is, so the very first thing we said was compact implies bounded. No. Yeah, that was the first thing in Rn. And then what we just showed was compact implies closed in any Hausdorff, which does include Rn. All right. The whole Heine-Borel, remember, is compact if and only if closed and bounded. So far we have shown compact implies bounded and also compact implies closed. So that's half of the Heine-Borel. The other direction of the Heine-Borel would be closed and bounded implies compact. So let's see if we can do that. Actually, that direction is not so hard by a cute little tricky trick. So I'm going to actually write it out here, the Heine-Borel theorem. My old friend, Professor Irene Mulvey, did any of you know her? Yeah, she retired a couple years ago. She referred to this, she used to have a picture on her wall, or on her office door. Daft Poltern. This is how she liked to describe the Heine-Borel theorem. I don't know where she came up with this. She always said the Heine-Borel theorem is a deep and fundamental property of the real numbers. That's what this stands for. Deep and fundamental property of the real numbers. I'm going to change this. You know, she taught the real analysis class for a long time, so that's how she described it. I'm going to say like that. How about that, huh? Deep and fundamental property of the Rn. That's what we're talking about, Heine-Borel theorem in Rn. It says, if A is a subset of Rn, then A is compact if and only if A is closed and bounded. She had a picture of a green glass bottle of Heineken, which she scribbled out the kin and wrote Borel. It says Heine-Borel, and then she wrote this across the label also. It makes no sense unless it's explained to you, but yeah. All right. Irene's doing great, by the way. She just sent me a picture of her with Kamala Harris. She's she's become like an educational political activist, and she's the president of this national organization now. We're all very proud of her. She's trying to fight all the book bans and attacks on university tenure that's happening a lot these days. Anyway, this is the Heine-Borel theorem. So, like I said, we've already done basically half of this. The arrow that goes this way, if it's compact, then it's automatically closed and bounded. Bounded, it has to be Rn, which is fine. And closed, it has to be Hausdorff, which Rn is Hausdorff. So, I will say this direction of the if and only if. This is already done. It's just the other way, and actually the other way is a lot easier. This required sort of, in my opinion, the closed part of this argument is kind of tricky. The one we just did with the A's and the U's and the V's. But the other way is not so hard if you allow a tricky trick. This, I would say, is not exactly obvious, but it's not so hard to do. So this way, we assume A is a subset of Rn, and we assume that it is closed and bounded. All right? What does that mean? So bounded means that it fits inside of a ball, like one big ball contains all of A. Now this argument is actually a little bit easier. Rather than a ball, can I say it fits inside of a rectangular box? So since A is bounded, I'm just saying, like, whatever it is, it's bounded, which means it fits all inside of one big box like that. For what we're about to say, it's more convenient to use a square box rather than a ball. Since A is bounded, A is a subset, or I'll just say fits inside some big box. B, and what is a box in Rn? Any box can be written as a product of intervals. Like that one there is a product of whatever this x-axis interval cross with this y-axis interval. And in Rn in general, a big, say, three-dimensional box or whatever is a product of three intervals or however many. So I'm going to write this as the box is something like A1 comma B1 cross A2 comma B2. I'm going to do it with closed intervals, although it could be whatever. It could be open intervals. AN comma BN, like so. All right. A fits inside some big box, like that. Okay, this is because A is bounded. All right. Now it's just a matter of patching together some theorems that perhaps you have forgotten, but theorems that we have talked about in the past 2 weeks finishes the whole thing. You don't really need to make any new arguments at all. First of all, B, the big box, is compact. Now that has nothing to do with A. A is just inside of it. But B is compact. That's because a closed interval, one of these intervals is compact. A closed interval is compact inside of R. And we already talked about if you have a product of two compact things, then the result is compact. This was something we mentioned maybe last time. I don't remember. But this big thing is a product of finitely many compact intervals. So this B is a product of compact things because a closed interval in R is compact. I suppose by the R1 version of the Heine-Borel theorem, we already know that a closed interval is compact. So B is a product of compact things, so B is compact. All right. Can we just keep track of where we used our assumptions? All of this is just because A is bounded, all right? It is inside of B, and B is compact. We have not yet used the fact that A is closed, and for that, that's another theorem that we talked about before. If you have a closed subset of a compact, then the subset is also compact. This is something that we did maybe last time. I also don't remember exactly, but we talked about if you have a compact set and then you shrink it down a little bit, the shrunk version will also be compact provided that it is closed. All right, so that's what's happening here. So A is a subset of a compact set. That's the B, right? And A is closed. This is our other assumption in the Heine-Borel theorem. I'll underline it. So that means A is compact. This is by some theorem that we talked about last time. This was an old theorem, old meaning like last week, that says if A is a subset of B and A is closed and B is compact, then A is compact. So all of these things were nicely laid out before to make this proof work. All right? And that's the end, right? This is what we had to show. We assumed it's closed and bounded, and we had to show that it's compact. And that's what it is. All right? This is the Rn version of the Heine-Borel theorem. You know, in real analysis, you went through a proof of the Heine-Borel theorem, but that was only for R1. So this is take that, Irene. We did it in Rn. I'm sure Irene could have done this too. She was a topologist too, which is why I've never taught this class before. She always taught it. And then when she retired, they were like, "Oh, we'll give it to Sean Rafalski." So he taught it then, and then I'm the third choice, I guess. All right, excellent. We got about 15 minutes remaining. There's really one more topic that I want to talk about for tomorrow, and maybe I'll just give you a little teaser for today, and then we will finish it up tomorrow. So that's the end of the Heine-Borel theorem. I hope that you appreciate the deep and fundamental property of Rn. There was an important theorem about compact sets and continuous functions, which I would like to say a few more words about, and then I think that will do it for the semester, really. I mean, a few more words today and next time. Sorry, I don't want to get your hopes up about next time. I would like you to remember a theorem about continuous functions and compact sets. So functions and compact sets. The theorem was, and we already talked about this a few times ago, if f is continuous and A as a subset of X is compact, then f of A is compact. So a continuous function takes a compact set in the domain to a compact set in the range, in the codomain. This is a true fact that we already discussed. This actually the same theorem is true if you replace the word compact with connected. That's also a theorem, that if a set is connected in the domain, then it's connected in the codomain. This actually, though, about compact sets, and sorry, can I just remind us? If you're talking about connected domain means connected codomain. That's basically the same as the intermediate value theorem in calculus. We talked about that. This version with compactness, this is the same as another theorem that you know from calculus. This is a familiar calculus theorem. This is called the extreme value theorem. Maybe this is a little less familiar by name. The extreme value theorem. Anybody actually remember what that says? We don't usually use this name for it, but the extreme value theorem. Extreme value means it's about minimum and maximum values. So in a calculus class, this is the way that this is usually stated is, so the way we say it in calculus is if if A to B is a closed interval and f A to B to R is continuous. I would never write that in a calculus class, but that's because they think everything is to R in a calculus class, because it is. Anyway, if this is continuous, then f attains its maximum and minimum value. In calculus, this is usually referred to as the absolute maximum and the absolute minimum. There is such a thing as an absolute maximum and absolute minimum on the interval A to B. And usually in calculus, furthermore you say this value either it appears on one of the two endpoints or it appears on the inside at a place where the derivative is 0. We're not going to say any of that stuff in our setting, but this business about maximum and minimum value, that's what the term extreme value is about, the ones on the end, the maximum and the minimum. All right. Now, in calculus, this is what it looks like. In topology, it looks like this, though. So what I would like, and maybe I will save this for next time because we can't fit it in now. It's not going to take all of next time. We'll just have an abbreviated class meeting tomorrow. But I'm going to talk about what exactly is the connection between this and this. This theorem is really about compactness. So how exactly to make the connection will be our topic for next time. All right, I think I'll leave it at that. I would be happy to hang around for 10 more minutes and talk about the homework if anybody has questions. Otherwise, I will see you tomorrow.